Okay, this section is on balancing chemical equations. And our goal is to balance simple chemical equations. When we get to some of these, you're going to find out that they don't seem to be that simple, but trust me, they are. So, there is one rule for balancing chemical reactions, and there's one rule for not balancing chemical reactions. Here is the do. Do adjust or change coefficients so that the law of the conservation of matter is followed. Do not change the formula of substances. So let's look at balancing a chemical reaction. Hydrogen peroxide, H2O2, decomposes over time to become oxygen gas and water. So here's the reaction. Hydrogen peroxide, this AQ means aqueous or dissolved in water. And here, H2OL, that means liquid, and this means gas. So, this is what happens to your hydrogen peroxide after a time. And that's why there's an expiration date on your bottle of hydrogen peroxide. You can hasten this up by shaking it, and it will help turn it into water and O2. All right. So the word decomposes means that this does not have to react with another substance to change. So let's look at balancing this reaction. And first of all, we should notice that it is not balanced. On the left, we have 2 hydrogens. On the right, we have 2 hydrogens. On the left, we have 2 oxygens. On the right, we have 3 oxygens. It's not balanced. So let's look at the do. I quickly realize that if I have 3 oxygens here and 2 oxygens here, that what I'm going to need to do is find some sort of a happy medium between that. And it seems to me that if I put a 2 in front of the H2O, I'll end up with 4 oxygens, and I can easily get 4 oxygens by putting a 2 in front of the H2O2. Now let's see, how does that affect the hydrogens? Well, I end up having 4 hydrogens and 4 hydrogens, so it works out just great. Okay, so this is the do. Change coefficients. I changed the coefficient in front of hydrogen peroxide and the coefficient in front of water, and I left the coefficient in front of O2 the same. You'll notice for balancing, I left the states off because we don't need the states to balance this. I can always reintroduce them later. So here's the do not. So I have H2O2, and I decide, you know what? I don't like that extra oxygen. If I just erase it, it'll be balanced. This is a do not. Do not change formulas. So there are these things called combustion reactions. Generally, we think of a combustion reaction as the reaction of a hydrocarbon with oxygen produce carbon dioxide and dihydrogen monoxide, or water. So hydrocarbon, hydrogen and carbon, reacting with oxygen to make CO2 and H2O. For these reactions, you want to balance carbon first, then hydrogen, then oxygen. Also, this can be a combustion reaction, the reaction of other molecules with O2. Now, we're going to go ahead and balance a couple of combustion reactions. So this is a little ad hoc here. I'm just going to throw this in here. So let's look at the combustion of methane to form CO2 and H2O. So this is something you can do when you're balancing reactions, but you don't always need to do it. You can make a list of each thing. One, two, three, 1 carbon, 2 hydrogens, 2 oxygens here, and 1 oxygen here for 3. 1 carbon, 4 hydrogens, and 2 oxygens. When you balance these hydrocarbon reactions, you want to do carbon first, then hydrogen, then oxygen. Just think about it as alphabetical order. The reason you do oxygen last is because if you have any element in the chemical reaction, a pure element, You want to leave that for last because you can change its coefficient and it doesn't mess up everything else. All right, so we have 1 carbon on each side, 4 hydrogens and 2 hydrogens. So what I'm going to do is I'm going to put a 2 in front of my H2O, and I'm going to count everything again. 1 carbon, 4 hydrogens, and 1, 2, 3, 4, 4 oxygens. So this is closer. So I see I need more oxygens over here, so I'm going to put a 2 here, cross all these out, count again, 1 carbon, 4 hydrogens, 4 oxygens, and you can see it's balanced. You'll notice my lists are the same on each side. Imagine if I had done this. Well, actually, forget that. Let's try another one. There is a compound called butane from butane lighters that has the formula C4H10. Whoops, I don't want a 2 there yet. So I want to balance this. And this time I'm not going to make a list. I have 4 carbons here and 1 here. So I'm going to put a 4 there. So now the carbons are okay. Now I'm going to go with the hydrogens. I have 10 here and 2 here. So I'm going to put a 5 here. So now we have 10. So double checking, we have 4 carbons, 10 hydrogens. When we look at the oxygens, here we have 4 times 2 is 8. 5 times 1 is 5. So 5 plus 8 is 13. Over here I have 2 oxygens. Here I have 13. What's the happy medium between those? Well, I can't get 13 oxygens when they come in 2s. So when you run into something like this, what you automatically want to do is just cross this all out and double all of the coefficients except for oxygen. And remember, when we double all the coefficients, we're keeping the ratios the same. But it's going to make it easier for us to figure out how many oxygens. And we'll see what happens here. How many oxygens on the right now? 8 times 2 is 16. 10 times 1 is 10. 16 plus 10 is 26. How do we get 26 oxygens when they come in 2s? We just need 13 of them. Okay? So this is balanced. Another way to do this is you get to here. And remember, we have 13 oxygens here and 2 oxygens here. So how can you get 13 oxygens? Well, you could do this, 13 halves. Well, we don't like balanced reactions that have half of a formula. So how can I keep these ratios the same and get rid of the half? And the answer is double everything. And there you go. So you can do either trick, realize that you're going to have to double down and then figure out the oxygens, or go with the half-Cs and double everything. Okay, let's take a look at, well, we've already seen this. Let's take a look at this particular problem. Balancing an equation for a combustion reaction. So write the balanced equation for the combustion of ammonia gas to give water vapor, so that's gas, and nitrogen monoxide gas. So here's the ammonia gas plus oxygen, because we're combusting it with oxygen, to give water vapor plus nitrogen monoxide gas. Okay, so in a case like this, what I normally start with is the first element I run into. One nitrogen, I'm good. I'm going to leave the oxygens for last because I have pure oxygen here and I can always mess with that later. 3 hydrogens and 2 hydrogens. So this is kind of weird. I can't just double these. That doesn't work, but we have to have a happy medium between these. And when you see something like this, what you want to do usually is find out what these will both factor into, the lowest number they will factor into. And the way to do that is multiply them. What is 3 times 2? 6. So let's go for 6 hydrogens on each side. So if I put a 2 there and a 3 there, I'll have 6 hydrogens on each side. But you notice when I put the 2 there, I changed the number of nitrogens, so I have to revisit that. So now I'm going to put a 2 here so that I still have 2 nitrogens on each side, so they're matched. 2 times 3, 6 hydrogens. 3 times 2, 6 hydrogens. So how many oxygens do we have? We have 2. Over here we have 3 plus 2, so we've got 5. So we've got this kind of, even odd thing going on again. So I think what I want to do is say that I want 5 halves, because 5 halves times 2 gives me 5 oxygens. And then I double everything. You always want to leave a nice space between your coefficient and your oxygen so that you don't think it's they're combined together into a number. Oops, that shouldn't be 3. I need to double it, so that's 6. And there's your answer. Okay, so here's some more problems. Write balanced chemical reactions for the following. The reaction of aluminum and iron 3 oxide to form iron and aluminum oxide. So here's aluminum. It's a metal, it's a solid. Iron 3 oxide is iron 3 plus and O2 minus. So that means the formula is Fe2O3, and since it's an ionic compound, it'll be a solid. To form iron, so Fe, solid, plus aluminum oxide. Well, aluminum is plus 3, and oxide is minus 2, so when I do the switch and simplify, I get Al2O3, and since it's ionic, it's also a solid. So this makes us use information that we learned in the previous chapter or module, and you still need to know that. Okay, so here we've written everything out in their proper formulas, and now we go set about balancing. 1 aluminum, 2 aluminums. I'm going to put 2 here. 2 irons, 1 iron. I'm going to wait on that, and I'll be honest and tell you why. Because I have iron here by itself, and I can always put the number in front of here and change it without affecting anything else. So I'm going to leave that to the end. So I'm going to look here, and I have 3 oxygens and 3 oxygens. And so now I'm going to deal with the iron. I'm going to put a 2 here, and it works out. 2 aluminum, 2 aluminum, 2 iron, 2 iron, 3 oxygen, 3 oxygen. It's balanced. So the reaction of carbon and water at high temp to form gaseous CO and H2. Well, carbon is not one of the diatomics. It's a solid at room temp. Water is H2O, and because they say water, not steam or not ice, it's a liquid. Now, of course, when you raise this to high temp, that's going to turn into a gas. We form gaseous carbon monoxide and H2 is a gas at most temperatures. In fact, you can't find H2 not in the gaseous form on Earth. It doesn't get cold enough, except for in a lab. Okay, so here I'm going to leave carbon for last because it's pure, and maybe hydrogen for last too. So let's go for the oxygens first. We have 1 oxygen, that's good. 2 hydrogens, that's good. 1 carbon. Boom, we're done. This is balanced. Okay. The reaction of silicon tetrachloride and magnesium. Oh, I'm going to put solid here. I'm going to cross that all out. Magnesium, forming silicon, and magnesium chloride. So magnesium chloride, we know it's made out of the magnesium ion and the chloride ion. So when I have the charges on both of these, I do the little switch and I get MgCl2. Okay, here, let's just start with what's on the left. Silicon matches silicon. Chlorine does not match chlorine, so I'll put a 2 there. I don't need to go back to silicon because I didn't change a coefficient in front of anything with silicon in it. So now I have magnesium 1, 2 magnesiums here, put a 2 there, and it's balanced. So you might be wondering, what's the real trick to balancing chemical reactions? Because this seems just like trial and error, and you just got to figure it out, and you have to grind it out to figure out the answer. What's the real way that chemists balance chemical reactions? Well, I'm going to show you. So here's another one where we need to balance. Here's how we chemists really balance chemical reactions. You see how we have 2 chromiums here and 1 here? We'll put a 2 there. Now here you see we've got that even odd thing going on that kind of is hard to deal with. So we've got 2 and we've got 3. And so here, I think what I want to do here is to get 3, I'm going to put 3 halves, because 3 halves times 2 is 3. Then I'll double everything. Again, leaving space there so we don't think that's 30. Then I'm going to go back and check. 4 chromiums, 4 chromiums, 6 oxygens, 6 oxygens, we're good. So that's the way we really balance these things. Trial and error. You just give it a try. Okay. Next, 2 coppers, 1 copper. So I'm going to put a 2 here. 1 sulfur, 1 sulfur. That's good. 2 oxygens, 2 oxygens. That's good. We're done. This one is a little more complicated because if you take a look at this formula here, there are actually 7 carbons, 6 here and 1 here for 7 total. So we have to be aware of that. We have to look at the detail. So I have 7 carbons here, so I'm going to put 7 over here. How many hydrogens do we have? 5, 6, 7, 8. So I'm going to put a 4 here so that we also have 8. And now for the oxygens, we've got 14 oxygens here, and we've got 4 oxygens here for a total of 4 plus 14, which is 18. So to get 18 oxygens, I need a 9 here. And I'm going to leave a little space there between the 9 and the O so it doesn't look like 90. And here's your balanced reaction. So be wary of formulas where they have the carbons and hydrogens spread out like this. You have to make sure you count correctly. Okay, so here's our last page of balancing. Now, if you were really a good student, you would have been doing this the whole time. You would have pushed pause on the video and you would have tried to balance each of these on your own. And then you would have looked at what I did and seen and compared the two and see if we came to the same conclusion. So I'm going to give you an opportunity to turn off the video, pause it, and when you pause it, you'll be able to see all of this. Write these down, give them a shot, and then compare them to what I'm going to do. So hit your pause. And you're back. Good. So did you have any problems doing them? I hope not. Let's take a look here. So we have Fe2O3 plus magnesium gives you MgO plus Fe. So 2 irons here. I'm going to put a 2 here to get 2 irons. 3 oxygens here. 1 oxygen here. So I'm going to put a 3 here to get 3 oxygens. And here I have 3 magnesiums, so I'm going to put a 3 here. Okay, moving along. Well, let's double check it. 2 irons, 2 irons, 3 magnesium, 3 magnesium, 3 oxygen, 3 oxygen. We're good. Let's take a look at this one. Now this one's kind of interesting because if you notice over here we have this OH and over here we have this OH. Those are the hydroxide ion. And there is nothing else with O and H in it. So I can actually balance this based on OHs. So let me show you what I mean. I have 1 aluminum here and 1 aluminum here, so that's good. I have 3 chlorines here and 1 chlorine here, so I'm going to put 3 there. I have 3 sodiums here and 1 here, so I'm going to put a 3 here. And now I have 3 hydroxides. I can pretend there's parentheses around that and see that if I have a 3 here, it's 3 of those, and here I have 3 hydroxides. So this is balanced. Let's see if we can do the same thing down here with this nitrates and the sulfates. So here we have 1 sodium, 2 sodiums, so I'm going to put a 2 here. I have 2 nitrates and 1 nitrate, so I'm going to put a 2 here. I have 2 hydrogens here, 2 hydrogens here, 1 sulfate and 1 sulfate. It's balanced. Now, can we get away with this down here? Well, maybe and maybe not. Certainly with the NO3 we can, because I see NO3 here and NO3 here. But do I see CO3 here and CO3 over here? And the answer is I don't. So I can't get away with that. So let's balance this kind of the older way, or a combination of ways. So nitrogen, nitrogen, excuse me, nickel, nickel, that works. Carbonate, well, 1 carbon, 1 carbon, that's good. Oxygen, you know what? It looks complicated, so I'm going to hold off on the oxygen for just a moment. Well, we can try. There's 6 here, and here there's 6, 7, 8, 9, so I'm not quite sure what's going to go on there. So let's skip from the oxygen to the hydrogen. 1 hydrogen here, 2 there. Let's put a 2 here. 2 nitrates here, 2 nitrates here. That looks good. Now let's go back and work on the oxygens. 3 here, 6 here for 9 oxygens. And here we have 6 oxygens, 2 oxygens, 1 oxygen for 9. So we're balanced. So it's okay to bail out on a tough element to balance and do something easier. And then maybe you'll just get lucky and it all just comes together. So that's the end of this section on balancing reactions. Thank you for listening, and try some of those problems at the end of the book.